In this video we're going to start the new topic of integration. So just a few introductory points and tasks to start off with. Now we've previously learned how to differentiate terms, so we know that if we've got f of x equals x to the power n, then the derivative f dashed of x is n multiplied by x to the power n minus 1. So we know for differentiating that we multiply by the exponent and then we subtract 1 from the exponent. So, say we're given the derivatives of some functions here. Are we able to find the original functions? So these have already been differentiated. What was the original? So maybe it would be a good time to pause the video and have a wee try at some of these, try and work out what the original functions were. If you can't get them, don't worry, that's fine, come back and we'll go over them. Okay, welcome back folks. So hopefully you've managed to get a few answers here. If not, like I said, don't worry, we'll go over these. So the first one here, before it was differentiated, we would have had 3x cubed. And you can see here to differentiate it, we would have done 3 times 3 to give us the 9, and then we would have subtracted 1 from the exponent of the x cubed to give us x squared. The next one, the derivative was negative 8x to the negative 3. So originally that would have been 4x to the negative 2. So the negative 2 would have multiplied the coefficient of 4 to give us the negative 8. And then we would have subtracted 1 from x to the negative 2. Subtracted 1 from the exponent of that to give us the x to the negative 3. The next one, the derivative is 5. So that means that the original function must have been 5x. And here, the last one, the derivative is 0. So that means that the original function must have been a constant term. So any constant differentiates to give us 0. So we've managed to find these original functions. So what have we actually done here? You might have noticed for differentiating, we're subtracting 1 from the power. So what's happened to go back the way we've added 1 to the power. And you may have noticed something going on with the coefficients as well. So let's generalise what's actually going on here. We're looking at integration, folks, which is another branch of calculus. And you might have already noticed from this task here, where I'm talking again about derivatives, that integration is the inverse of differentiation. Now, integration, if we've got the function x to the power n, we want to integrate that with respect to x. Like I said earlier, we are adding 1 to the exponent of x to the power n, so we get x to the power n plus 1. And then we're actually dividing by that new power, that n plus 1. And we've got this plus c here, and we'll talk about that in a wee second. So a few things to point out at this stage. This here is the integration symbol. It's almost like a big S that's been stretched vertically. We must show when we're integrating something, so we need to remember and use that. We then have this dx. Now that'll be familiar to you. When we were differentiating functions, we might have written dy by dx, and that showed that we were differentiating y with respect to x. So by putting dx here, following the integration symbol and the function, it shows that we are integrating with respect to x. And finally, we've got this plus c, and that is the constant of integration, and it represents constant terms in the original function which would have differentiated to give 0. So if you remember back, any constant, say it was 5, that would have differentiated and given us 0. And when we're going back from 0, we're not quite sure what that would have been, so we're just going to call it c so that we're generalising that. Any integral which has the constant of integration at the end is called an indefinite integral. So that's what we're going to look at just now, and we'll take a look at some examples here. So the first example, we want to find the integral of x squared with respect to x. So if you remember what we were doing, we were adding 1 to the exponent of x squared. So that gets us x cubed. And then we were dividing by that new exponent. So it's x cubed over 3, or a third x cubed. And then we have this constant of integration as well. And that's our final answer. Second example, we want to find the integral of x to the negative 3 with respect to x. So again, we're adding 1 to our exponent, so that will give us negative 2 for our exponent, and then we need to divide throughout by that new power, negative 2. So it's x to the negative 2 all over negative 2 plus our constant of integration. And we might want to express that with positive indices. So x to the negative 2, remember we can express that on the denominator of a fraction with a positive index. So it's negative 1 over 2x squared plus c. And the final example, we want to integrate x to the 5 quarters with respect to x. So remember we have to add 1 to our exponent, so that will give us x to the 9 quarters, and we divide by that new exponent. So it's x to the 9 quarters over 9 quarters plus c. And remember folks, dividing by 9 quarters is the same as multiplying by the reciprocal. And the reciprocal here is 4/9. So this is the same as multiplying by 4/9, as you can see here, and we can express our x to the 9 quarters with a radical sign. So it's the 4th root of x to the 9 plus c. So it's 4/9 of the 4th root of x to the 9 plus c, and that's our final answer. So it would be a good time to pause the video just now before the screen goes blank, and take these notes down in your notes and make sure that you complete the assigned exercises for today to go along with the notes so you're practicing these questions.